Hi and welcome back to your chemistry lesson. We're looking at the Chateliers principle, and let's just read it again. It says that if a stress is added to a closed system in equilibrium, the equilibrium will shift in the direction that will relieve the applied stress. And we looked at, for example, at temperature and how temperature affects the stress. So if temperature in a reaction was increased, then it depended on whether it was an endothermic or an exothermic reaction. So endothermic means that we needed energy, so enthalpy is positive, because enthalpy is literally how much energy do I need. So an endothermic reaction, temperature is a product, a reactant. If I increase the temperature, then the forward reaction is favored. And the reason for that is if I increase the reactants, then there are more reactants to react, and that will produce more products. So I am favoring the products, the forward reaction. If I have, however, a exothermic reaction, how much energy do I need? Well, I don't need energy, so it's a negative value. I am expelling energy from the system, or releasing energy, which means I am producing, if temperature is increasing, I'm adding more products to the reaction, which will favor the reverse reaction, because products also react with one another to produce reactants. So if I add more products into the system, I will favor the amount of successful collisions that can occur in the products, which will create more reactants. So that would favor the reverse favored. Okay, I just wanted to summarize it here. Now let's look at what effect will a catalyst have. Okay, what effect will a catalyst have? Because now what we're going to look at is we're literally going to look at all the effects that things have that increase the reaction rate, because that's what we're trying to do. Le Chatelier's principle is applied to a reverse reaction. A plus B is a reversible reaction to produce C plus D, and we want to see what can we do to either produce more products or more reactants, okay, because we have a certain process. Now you'll remember that the effect of a catalyst was if I had whatever reaction, I had my internal energy of my reactants, I had my internal energy of the intermediate molecules, and then the internal energies of my products, and I would have some sort of a curve like this, and this would be my potential energy curve. Okay, and what a catalyst did is it reduced the internal energies for my intermediate, the internal energies for the intermediate molecule, which meant that the activated complex was reduced. The amount of that's the activated complex, and now we can see we've got a lower activated complex. The amount of activation energy that we needed to add into a system in order to produce or for the reaction to start occurring is now being reduced. So that is why the reaction rate increased, because we don't need as much energy for reactions to occur, because the intermediate molecule doesn't need as much energy. Okay, so more successful collisions happened because I didn't need as much kinetic energy among my molecules. But now I want you to notice that this was for the forward reaction. And now for the reverse reaction, I'm literally just looking at this direction. I'm literally inverting this graph, so I'm not going to draw it, otherwise it will mess up this picture even more. But for the reverse reaction, this is the activation energy, and if I now reduce it, my activated complex, this is the activation energy. So notice that for both of these, my activation energy has been reduced. Okay, so when adding a catalyst, it doesn't have any effect. The effect that it has on the forward reaction and the effect that it has on a reverse reaction is exactly the same. Both reactions are increased, okay, the rate of reaction, because both have more successful collisions, but the net change is not affected. Okay, so a stress is not added to the system, a stress is relieved on both sides, so adding a catalyst has no effect. Has no effect on the equilibrium. On equilibrium position. Okay. The next thing we can look at is if we increase pressure. So what happens if we increase pressure or volume? Now, how do I increase pressure? I increase pressure by decreasing the volume. So increasing pressure and decreasing volume is exactly the same thing. Okay, to make something have more pressure in it, for example, think of a balloon or something. If you were to push a balloon between your hands, you are increasing the pressure of the molecules inside the balloon, and because you are trying to decrease the volume. Okay, now what effect will that have on the system? Now you'll remember that when it comes to the reaction rate, increasing the pressure or the volume has a direct effect on the reaction rate where gases are involved. Okay, and that is because, and let me draw an example here. Okay, that is because if I have a container and I had gas particles in here, then if I reduce the volume of that container, okay, and I have the same number of gas molecules in here, the neighborhood where those gas molecules now have to freely roam without bumping into one another are fewer. So the likelihood of successful collisions are higher, okay, because there's less space to have no collisions. And therefore, when we increase the volume, we are literally causing more successful collisions among gas particles. Okay, now that is why when we increase pressure or volume, in order to understand the effect that Le Chatelier's principle has, we have to go in and look at the moles. And I've told you before, I like to put little lowercase letters in front here to represent the moles. Okay, if A plus B, okay, let me rather do this. A gas plus B gas is greater than C gas plus D gas. Okay, what I mean by this is I'll only look at the coefficient of the compound if that compound is a gas. Okay, I'll give you some examples in a minute. Okay, but if this is a gas, then I'll take the coefficient, and if that is a gas, I'll take the coefficient. But basically what I'm doing, I'm adding up all the coefficients of gas reactants. And if I have a gas, then I'll add the coefficient, and I'll do the same on the other side. The side that has the most, so for example, if the reactants have the highest moles of gas, then by increasing the volume, I am causing this side of the reaction to have more successful collisions because it has more of it is gas. So if there's more successful collisions between the reactants, I am favoring the reaction that goes in this direction. So then an increase in volume or pressure will favor forward. Will favor the forward. Now notice how Le Chatelier's principle applies here. We are adding a stress to the system. Okay, and in the system I have more reactants that are gaseous. Now if I increase the pressure, or if I decrease the volume, I am putting a stress more on this side of the reaction, because this is the side that's taking the most space. Gas takes more space than liquids and solids. This is this side that has the most gas. Now, in order to relieve that stress, we will produce this part of the reaction will react more to produce rather more of this, which has less gas. Okay, that's now in this example. If I add up the coefficients and I find that the forward reaction, the products have less gas, then I'll rather produce more products, because that will relieve the stress that's on the system, because there's more gas or more space is taken up by the reactants. Now if it was the reverse case, so in other words, if I had that my coefficients for all the gas reactants are less than the coefficient for all the product reactants, then obviously the exact opposite occurs. Now if I increase the volume, now I will if I increase the pressure or decrease the volume, I will put a stress on this side of the reaction, because this side of the reaction takes up more space. Okay, so if I decrease the volume, we want less of this to relieve that stress, and we'll produce more of that, which means we will favor the reverse. We will favor the reverse reaction. Okay, now let me give you an example that we have looked at already, and that was the reaction between this NH3, and here we had 2 of these and 3 of these. Now notice all of this would be gas. All of these are gases. Okay, and on the left hand side we have a total of 4 moles of gas. So 1 plus 3, 4 moles of gas, and on the right side of the reaction we have 2 moles of gas. We're looking at the coefficients. So in other words, if we reduce the volume under which this reaction is occurring, we are definitely favoring the forward reaction, because in order to kind of balance out the best scenario by decreasing the volume, to balance out the best scenario, more of the gas in this reaction will react with one another to produce more products, so that the stress is being relieved. This takes up too much space. Okay, so by increasing or decreasing the volume, more of these molecules will react with one another to produce reactants that take up less space, and therefore releasing the pressure. I hope that makes sense. I really don't know how else to explain it. Okay, but that would be the effect of pressure or volume in the system. Now let's look at the third one would be, the fourth one would be increasing concentration. Okay, increasing concentration. Now, hopefully what you'll be getting so far in both temperature and in the pressure and volume or pressure or volume change is that when I increase reactants, When I increase reactance, I'm favoring the forward reaction. When I decrease reactance, I would favor the reverse reaction. When I increase products, okay, I put more of the products in the closed system than I had before. That means there's more likelihood of successful collisions in the products, which means I'll favor reverse reaction, the reverse reaction rate. If I decrease the products, okay, if I decrease the products, I would favor the forward reaction, because the percentage of products compared to the percentage of reactants are now less. So the reactants have a higher likelihood of successful collisions than the products have, making it favor the forward reaction. Now the same goes now for concentration. Literally what we mean by when we say if we increase the concentration, it means that if I increase the percentage of reactants, however I do it, if I have, for example, in this reaction that I have here, if I were to increase the amount of nitrogen that is in the closed system, it means I'm increasing the concentration of nitrogen in the system, the amount of nitrogen that I find per volume unit or whatever. Okay, so concentration is moles per volume. So if I increase the concentration of nitrogen, it literally means I'm increasing the amount of moles of nitrogen, which means I'm adding reactants into the system. If I add reactants into the system, there's more likelihood of successful collisions on the left, which will provide more reactants, more products. Now, in terms of Le Chatelier, how does that explain Le Chatelier? Le Chatelier says we're adding a stress to the system by adding more reactants. In order to relieve that stress, we must use up the reactants and therefore produce more products. Okay, so when increasing the concentration literally says that if I increase the percentage of reactants or the concentration of the reactants, I will favor forward. Okay, obviously if I decrease, okay, we're looking at increasing concentration, so let me not say that. So if I increase the percentage of products, well then obviously exactly the opposite happens. I favor the reverse. Okay, and these are going to be the 4 changes that we look at, and briefly again, temperature. An increase in temperature will favor the forward if it is if temperature is a reactant. Temperature is a reactant in endothermic reactions, in other words, reactions where I need energy, so my enthalpy is positive. Okay, catalyst has no effect. Changes in pressure and volume favors the side with the least. Okay, so let's write it here. Favors the side with least moles of gas. Okay, that makes sense. Okay, it favors the side with the least mole of gas. So if my products have less gas and I increase the pressure, then I'll produce more products. Okay, so equilibrium will shift in that direction. Increasing concentration always has the opposite effect than the side that I'm increasing. So if I'm increasing the reactants, I'll produce more products. If I increase the products, I'll produce more reactants. And that's basically it. And using Le Chatelier to explain that effect simply refers to adding a stress to the system will have the effect that the system will react in the opposite direction to relieve that stress. Thank you very much for watching. I hope this made sense to you, and we'll see you in the next video where we will look at the reaction rate graphs, or not reaction rate graphs, the mole versus time graphs, and how we can see what effect changes has on that graph. We'll see you there.